Food drying is important to avoid crop typical losses that on the developed countries can be as high as 50% and even higher. So solar drying is very important and is sustainable and keeps the quality of food. So somehow solar air heating, a solar air heating collector is necessary. Avoiding electricity is paramount, so that for remote and isolated communities, even photovoltaic electricity should be avoided. The solution is using natural flow because hot air floats with natural air motion, and this is possible, of course, and theories helps how much can we get from that, and on what variables it depends. And what is also important is to keep drying during the night. And the solution for that is to keep some heat, some thermal energy storage, TES, that continues to heat air without the sun. Well, it is difficult to model a solar air heating collector. On the left side, you can see the cross-section of a typical indirect solar dryer, where you have a cabinet with the food that you want to dehydrate, and you have the solar air heating collector that is of a length L, that inside it you have the air velocity here in meters per second, that is heated by the solar irradiance G, that is watts per square meters, and you heat the air between an inlet temperature and an outlet temperature. Of course, for producing this draft, this natural draft, you have an inlet that is at a lower height than the outlet. What I can see you is that we avoid this part, the cabinet, because we are interested in simulating and modeling the heating of the air in the solar air heating collector. For that, we developed a prototype that you can see here, open and without the glazing, and inside we put more than 100 beverage cans that are commercials, occupying a width W, and of course these are at the same time the solar absorber and the thermal energy storage. What you can see here also is that there is a flow between two parallel plates, that is the glazing and the cans. On the left you can see the first prototype, and we discovered that there are large homogeneities in the flow because it is an open inlet and an open outlet, and the wind makes a lot of influence. On the two images on the right, you can see the second prototype that avoids the cabinet and has a tall chimney of circular cross-section, and there is a nozzle here where we measure the air velocity. You can see here the blackened cans and a central spine for avoiding the air going laterally. Okay, so the point is that we will study this prototype in this presentation. Now here is the theory of this solar air heating collector. On the right images you can see here the cross-section for the air flow that is between the glazing and the upper part of the can. One important parameter in the flow of air is the Reynolds number. The Reynolds number explicates the relation between the viscosity forces and the inertial forces, and we have a very low velocity of air inside both plates, that is between 0.1 to 1 meter per second, and actually 1 meter per second we haven't now registered perhaps half of it. The Reynolds number, when it is low, the flow can be supposed to be laminar. When it is lower than 2000. And here you have the calculation of the Reynolds number for a height of the air cross-section of 3 to 5 centimeters, and gets this expression that is directly proportional to the air velocity, times a number that is perhaps near 5,000. But if you multiply by 0.1, you get 500. That is much less than 2,000, so that we can say that the natural flows can be laminar. The heat transfer between the cans and the air can be modeled using a heat transfer coefficient H times the average difference in temperature between cans and air, and this is the solar power over the area of the cans. The area of the cans, as you can see here, is a little higher than the glazing area, and typically the heat transfer coefficient is calculated using a non-dimensional Nusselt number times the thermal conductivity of air over H. So if we put all of this and we assume that if the flow is laminar, the Nusselt number by theoretical calculation is slightly higher than 8 times 5, we arrive that the average temperature of the can is around 70 degrees. So it doesn't boil, it doesn't explode, the cans doesn't explode because there is only water inside with tea and there is no carbonated beverage. So this is safe. The pressure drop is very important because as an action of the viscosity, the pressure downstream, the flow is reducing, and typically this pressure reduction is modeled as a friction coefficient times the length over the H and times the dynamic pressure. This is very low, around 1 Pascal, so measuring it is extremely difficult. Because the flow is laminar, there are expression of the friction coefficient of both the plates and the chimney that is 96 over the Reynolds number and 64 over the Reynolds number. And of course, the chimney has a friction coefficient that can be assumed as similar to the cabinet. Okay, the length that we use is around 2 meters, and the density of air is around 1 kilogram over 1 cubic meter. So at the end, what we have is that the K uppercase K, that is F times L over H of the plates arrives at this expression that is inversely proportional to the velocity times L over H squared, and for the cabinet or for the chimney that is very similar also gets an expression that is very similar to the plates. So we can model in approximate way how is the pressure drop around the whole flow of the solar air heating collector. Now if we apply the one-dimensional steady-state momentum equation of the flow through the solar air heating collector, we arrive at this expression of the air velocity, where k is much higher than 1, so we can neglect 1 in front of k. The average temperature of the air is modeled here, and the mass flow rate is this here, that is constant along the solar air heating collector, and Cp is the air constant pressure specific heat is 1000. Average rho is very near the atmosphere density, and K is the addition of the one of the plates and the one of the chimney or the cabinet that is very similar. So we add them and we see that it is proportional to a K total over the air velocity times L over H squared. And if we apply the energy conservation, the power applied to the air flow is times the efficiency times the solar irradiance and times the aperture area, that is L times the width. And eta is around 30 to 50%. So if we introduce all that on this equation, we get finally the expression of the air velocity that is clearly says that the air velocity is proportional to the square root of the height between inlet and outlet, of the efficiency of the irradiance, and curiously it is also times h here. So as wider it is the inner flow because of the cross section, it is better. What is striking is that it doesn't depend on L. So if we increase the length of the solar air heating collector, we don't get higher velocity. Also, we want velocity because it's quite low to increase it as much as possible. Because of that, we avoid the perturbation of the external wind, and also we increase the heat transfer from the food pieces. We have developed not only the theory but also experimentation. Because the flow velocities are so low, we had to buy a probe for air velocity and an anemometer that you can see here that can measure velocity as small as 0.1 meters per second. What you can see in the central figure is that this is the air temperature increase, and going to the sunrise, we see that it increases typically, and it goes to the maximum in the afternoon, and during the night it decreases very slowly because of the thermal energy storage. And what is good is that we maintain a temperature increase higher than 5 degrees up to 4 a.m. I mean, this is a.m., not p.m. What is good? And it goes to 0 down to the sunrise. So we get with the thermal energy storage a good temperature increase almost for 20 hours in a typical day. What you can see here that there are different days. This is from 11th to 16th of June here in Madrid, and you can see that there are some singularities. For example, a drop in delta T down to 0, and even negative because windy and cloudy period, and also in other instances. As you can see here in the lower figure, is that theory says that delta T is proportional to G, the solar irradiance over the air velocity. And with equation 4 of the previous slide, the air velocity is proportional to the square root of G. So we end up that the air velocity is proportional to delta T. Is this true or not? You can see in the lower graph that you have the air velocity that you can see that quite low, below 1 meter per second, and in the horizontal axis you have delta T, and you see a lot of dispersion because of the effect of wind, but there is an increase, a linear increase, as we expected with the theory. So that as the main conclusions, natural draft can be used to dry food indirectly. The size is the width of the solar air heating collector, and secondarily H, the height. Heating is proportional to the length over the air velocity. That says that increasing the length is good for the increase in the air temperature. And for maximizing the air velocity, we need tall and insulated chimneys, smooth and tall aerodynamic inlet conduits, because if otherwise K will increase and a high efficiency. So that we need to have a high optical and efficiency, and also have a very good insulation. No windy locations are desirable because otherwise we have perturbation. If you need more information, you can see here some help of previous congresses. Well, thanks for your attention, and here you can see 2 books that you can get for free as a PDF that I have written.